Okay, hello.
This part of the blackboard is going to be in the view.
Okay. I will tell you about robust constraint control, Zonotope approach. After lecture, you should understand how control system in this form, task of trajectory tracking. Here in the system, several moments that difference from conventional way. A and B, it's a sets, and additional disturbance, it's sets too. It happens when you don't know precise your parameters. For example, you don't know external disturbance, but you know that it's bounded, and parameters of your system too, you don't know, but you know some limits. When it's happens. For example, in more trivial case, it's unknown payload for manipulator. You know some limits, but that's all. But it's not. It's a more simple example, but not the full. Several days ago, I read several papers about rocket landing, and they describe the systems in this way too, this form, because parametric of atmosphere not simple and can be very fast changed. They solve this task in this form. It was rocket landing in the Earth, and some spaces landed on another planets. Another examples, for example, in self-driving car area, who interested in self-driving car area, yeah, some people's. When you you should design some reactive motion of your car, but you don't know how many people's inside and ways of these peoples. And yes, you can be model of your car can be very precise, but you haven't model of your passengers. And if you need make very reactive movement, and you have very hard constraint, it's the size of your rod, you need to model in something like this form. Another example, it's about identification. You can see a very simple system. It's inverted pendulum with elastic wall. It's a real system exists in our lab. It's actuator, aluminum rod, external additional payload, and spring. And this system can be described very easy in this form. It's a hybrid system in contact mode and without contact. It's two equations, and this very simple equations. But if we look more detailed and try realize this control on this system and satisfy some guarantees, we can see a very interesting moment. For example, mass. Yes, we can very easily find mass of the system. Additional mass, aluminum rod, no problem. Length, very easy too. But next step, we try to find inertia parameters of this system. If our system have a very easy shape, yeah, we can. But when our shape of movement part start to be more complex, we need identification. And we cannot calculate it. We need to identify it. Someone know what's identification of system who have experience in that? No. You hear about this procedure?
Yes.
It's very non-trivial, it's very tricky, and your identification practically always not so excellent. Simeon sometimes can make a good identification, but main part of overlap, no. And you inertia that you get in identification, it's something very not precise, but you always can bound it. Maybe it's between Z and Z. Next, spring. Spring is linear, but in this case, for example, pendulum contact spring not at the right angle, as the angle changed during the motion, and based on it, this part start to be non-linear, and friction in contact very non-linear. I try to identify it in this form, but it's too very not precise. And after that, you cannot describe precisely motion of the system in this form, but with boundedness. But you can tell that parameters between Z and Z. It's last part of examples. No, we finished that. Who have ideas how we should control our system when we don't know precise our parameter? Who have ideas?
Process control. Process control.
Yes, but what's control? PID regulator. PID regulator, it's a good idea, but not so well work on trajectory tracking. When your system moves very fast and very rapidly, PID control not work so well. Adaptive, yes, it's a good idea. Adaptive control, if system parameters of system change slowly, it's a good idea. But for example, for some classes of system, for example, for underactuated systems, you know what does it mean, underactuated systems? Okay, adaptive control work very bad. You cannot make an adaptive. You cannot apply adaptive control for swing up of card pole or acrobat.
Or boss control with hardness spaces long.
I don't know what is it.
Infinity long.
As I understand it, I remember. As I remember, you cannot add constraints to this form. Yes. Okay, let's continue. If our set is relatively small to some parameters, for example, you know that you mass between 1 kilogram plus minus 5 grams. Okay, you can apply just LQR. If your system is as constrained, you can apply it, and in practice, it will work. But if the sets were big and you design your control for one point in this set, can you say your system will be stable for another or not? For example, if this parameters is relatively big, maybe your control stable for one point, but not stable for another, and it's don't work in this simple way. If you add constraint, if you need that constraint, you can realize MPC, but you know MPC, yes? You can add constraint, realize MPC, and it will work too, but only if this set very small and no guarantees, but something similar. Problem with MPC follows. If in start of moving your set is 1 point, After applied a set of dynamics, your system starts the set. It's not a point, it's a set. And when, sorry.
You can continue like explanations of Blackboard. Is the audio quality would be quite worse, but people will still be able to hear you somewhat. So
Maybe. Okay. It's your error time. It's 0 if you start, for example, from here, and your set increase, and at some moment part of your set on the one side of error and one on another, and you cannot choose one control action that satisfy this situation. It's a reason why you can't use MPC in a conventional way for this. Another solution is dual mode MPC or tube-based MPC. And you design some feedback gains, apply it to your system, and only correct. You build some constraints, start propagate your movement, and if part move to the constraint, you add some U additional. Yes, but problem with this approach, very similar to first idea. If you design your feedback gains for one system, it can be unstable for another. But it's very good approach. Another idea, it's Lmi based feedback. It's a concept how you can design your feedback that satisfy all your sets, but it works only on point. But yeah, to work very well, it satisfies. You can guarantee you can give guarantees. It satisfies your constraints, and its system will be stable. For example, limits. You have a road, car moving at the road, and you cannot cross lines. Or you have a manipulator and a wall. You should not push the wall. It's constraints. Or, for example, you are a legged robot, and for fall condition, it's a constraint. This example of a Z. After this little overview, we can understand that we need some design of feedback gains that stable for all our system, and all situations satisfies our constraints. First idea, it makes something very similar to MPC, conventional MPC, but choose K as decision variables. It's first naive idea, but this idea have a very big problem because it's a non-convex task. When you describe propagation of your state, you get multiplication between your decision variables, and it's start to be non-convex. It's why we need some tricky approach to solve this task. And concept of this solution at recently big another approach for solving this type of systems. It's design state and actions in on the trajectories and find feedback after that. For example, in MPC, we very easy can find feed forward for one point. And here we can take several points, find feed forward for each of them, and based on it, find feedback gains. It's very different and very non-intuitive concept first times, but it's have a lot of advantages because you think not about feedbacks and agent values, you think about trajectories and how a system really moving. And because it's about sets, first we should describe type of sets that we will use. We will work with Zonotopes. Zonotopes, it's point symmetric sets in n-dimensional space. It's a very narrow type of polytopes, but this type have some very good properties. Let's start with several examples of Zonotopes and how it works, how we describe that. Sorry. For example, our state is, we know that our, we speak about pendulum, and we know that our angle between 1 and 1.2, and our velocity between 2.1 and 2.3.
Can you please use a different pen? Different mortar.
Okay.
It's not visible.
Yeah. It's better.
Yeah, that's good. Thank you.
By the way, feel free to come closer, everyone who ended up there. I mean, if you want to, of course, because I think this blackboard is not suited for viewing from.
Maybe it's our position between this 2 point and our velocity between this 2 point. We can find a center of this sets. It's Q center. It's 1.1 and Q dot center 0, 2. And it's Q center. And here you can see that Zonotope described as center as and as combination, linear combination of generators. You can take several vectors and build all the linear combinations with coefficients between -1 and 1. And here we center .1.1 0 and generator it dot 0.1 0. It describes difference, possible difference in Q, and 0 0.1 for Q dot. And first we take this vector, build them. We take this vector and describe set with multiplication combination of these vectors at -1 to 1. We get this and take second vector and add possible combination of this vector to z vector. And we get this area. We get Zonotope with center 1.1.0.2 and generator in this form. That described these possible states. Another example, Zonotope with center anywhere, for example, in 0, 0, 0, 0, and generator 0.5, 0.5, minus 0.5, 0.5, 0.1, 0. For example, another Zonotope. We can build it. Take first this vector, .5, combinations described like this. Next vector, minus .5 and .5. This vector. All combination of these two vectors described like this. And next vector, .1, 0, like this, and all those combination described in this form. And this Zonotope, as I said. Any question about Zonotope?
Just one question. We can things here. The generator, the first generator, the last element should be open O1.
Last element
Of this generator.
of the generator 0, 0.1. And
Yeah, it should be 0.01, right?
0.01.
0.01.
Why?
Because it's the distance in Q dot.
Yes, and distance between this point and this point, it's dot 2, and half of dot 2 is dot 1. All understand how we described and built Zonotopes.
I have a question here. This generator can be a nonlinear function of state, or it should be just a fixed values?
Fixed values. It can be function, but at each concrete point, it should be concrete values.
Yeah, but in principle, it can be some function that you evaluate on this state. So you got the measurements of state or whatever.
Yeah.
And then you can evaluate this G as a function, right?
Yes, it can change. So we can describe. Okay. We can something little later. I answer those questions.
Just to be clear, if you allow me. So the important part here is that this figure is a geometric figure that has to be a polytope. So whatever, when we say Zonotope, we should remember that it is not just a description with a generator in the center, but also a geometric figure. So it has to have like faces, edges, and so on. So whatever we interpreted it as, we should still remember that it is still just what is drawn there. So even if you consider it as a nonlinear function of state or whatever, at each point of time, this is just.
No, I mean just so about this basis. So can we shape it not as a fixed like shape, but use the basis some nonlinear functions?
Yeah, but this function is not going to be nonlinear in the space in where polytope is.
Yeah, sure.
Yeah. Sorry for interruption.
No. Okay. Yes. Yes, it's just very narrow type of polytopes, but we use them because this form have very good properties, and it's a Zonotope operation. First, it's linear transformation. If our state described in this form, and we apply some dynamics for this state, and we want to describe its k plus 1 as ax, where x our Zonotope, we just apply linear transformation A to center and generator. And very often we describe our Zonotope. It's, for example, it will be Zonotope P, and we describe P as x center J. This and we get A x center and A J. That's all. Very easy form. All understand. Only if you understand why this.
I don't understand what's A and.
A is your dynamics. For example, here your state of your pendulum. You want to describe motion of your state in future. Describe propagation, and A your dynamics equation, linear dynamics equation, and at k step your state is here, and k plus 1 step your state is here. Okay. No question.
Can the next state or the future state be outside of the Zonotope?
Outside of this Zonotope?
Yes.
Your state will be another Zonotope. For example, I don't need this. I will explain this. I show this example in future, but maybe it will be good at this moment. All of you know the equation of mass spring system. Okay. So okay, it should be mass spring network with friction, and our initial state x at moment 0 is Zonotope in this form, and when x tends 0, and after moment we get something like this. Next Zonotope will be this, and system converges to 0 based on that. It's okay. Answer a question. Next property is Minkowski sum. Minkowski sum is operation of summation to Zonotopes. For example, you have go to this example. Your state for your mass spring network area here, and you know that at each step you have some disturbance, and you know you don't know what is it, but you know that disturbance on each step is bounded by this Zonotope, and you want to add this Zonotope to this intuitively, it's described in this way. You get the Zonotopes. And for polytopes, summation between two polytopes is very difficult relation. But for Zonotope, it's just okay, this Zonotope was 1, 1, minus 1, 1. This dot 1, 0, 0, dot 1. And their sum 1, 1, minus 1, 1, dot. Summation of two Zonotopes is just a combination of their generators. And that's all. It's main reason why people work with Zonotopes. And last operation, it's a containment. How we can understand is one Zonotope inside another or not. It's these three operations. It's the main part that we need. Here, after that, we can describe system behavior with Zonotopes. We take a affine linear variant system in this form, and where x and control actions is Zonotopes. And Zonotope propagation just based on the first operations, linear transformation Zonotopes at step k plus 1, our center of Zonotopes. It's this operation, just the same what that will be with 1 point. And generator we just sum these generators. But very important point, it's not Minkowski sum. It's just the summations between vectors. And I explained this moment more detailedly, but after that, when we describe propagation of our Zonotopes, we can write optimization task that minimize our cost subject to our Zonotopes dynamics and subject to our constraints. Now I explain this moment and how it's happened in more detail. Our system is a mass spring system. Our initial state is in this form, described in this form. Our initial state described as Zonotope P0 with center 0, 0 and generator 1, 1, minus 1, 1. Our cost, for example, quadratic. We just in simple MPC. We want minimization of quadratic cost of our state and control actions. And we need some control actions for this vectors on each state, on each state that minimize our cost. How it looks like? At first step, after our dynamics, without control, system moves in this way. You understand this moment?
What's the inner circle?
It's как силовые линии называются по-английски, не знаю. Семен, ты должен знать. Ты должен?
Yeah. So this is a phase portrait, right?
Yes, it's a phase portrait.
Phase flows and flow works system.
Yes, yes, vector field of our system. Without control, point system moves in this way.
So what kind of system is this? MK?
It's
Okay.
when u equals 0, this system moves in this form. And we need to find u that converts this system to 0. And without some control, this and this point moves to a cycle.
And if we have a damper, we see a vortex.
Yes, but we now in this example we speak without damping. For these two vectors, we can find u that converts. And for example, at first step, without control, this vector moves at this point, but with control to this point, and this to this and this. And we can find u that make something like this. And it's the idea of our optimization task. Because it's not feedback, it's just feed forward. But each point of our Zonotope described as a linear combination of these two vectors. And any point, we can any point project to these two vectors, and later and after that speak about behavior of these projections. Its main idea of this concept that you can find feed-forward control, and based on this feed-forward control, find a policy for each point in this area. Just make matrix multiplication between generator delta K and the inverse of generator of our state. It's most non-intuitive and non-trivial part of this approach, but it's very conceptual and not formal way. It's like u equal kx, and you can find k multiply what it is main concept. Questions?
What is set h, x, k, and h? So
It's some constraints, limits, and another.
so it's some convex.
Yes, it's convex set, for example, you need some behaviors that don't cross these areas.
So it's your target set. You want to be in the set?
Yeah, no, it's just simple constraints. We speak not about infinite behavior only at some trajectory, only for same steps. Another question.
This is basically a QP, right?
Yes, yes. It's no. It's not QP. But it's convex. For example, if because as I remember, this part is SOCP, yes. Yep. Yes. And cost can be quadratic, cost can be linear, constraints can be SOCP, QP, and another. But it's in this form, it's convex and give you guarantees. For example, HU, it's limits of your control, and something, another if you need. So, questions?
What is the decay?
Theta K. Yes. Yes. The K is generator of controls on top. Theta K can consist all if at first step this vectors is G0, G1. G at point 0, it's G0, G1. At theta 0, it's control actions that solver gives for us. Should be theta, not theta, L, KL. L1, L0. It's this theta K solver gives for us after optimization task. It's optimal control actions for these vectors, and each not only for first 0 step or any step between 0 and K.
And this bar is meaning average.
It's Zonotope.
X bar means center.
X bar is at center, yes. It's at center of the Zonotopes and it's to the center of the Zonotopes. Yes, you can see it.
I thought it's nominal trajectory. So it's nominal trajectory. Physically, it's nominal trajectory.
It's the center of Zonotopes, yes.
Which is the same as nominal trajectory.
Yes.
For two-dimensional phase plane, a zonotope is a figure inscribed in a circle. Yeah.
Not circle. It's for two-dimensional system, for example, for two-link pendulum, n equal 4. It's a four-dimensional state, and it's a zonotope symmetrical polytope in four-dimensional space.
But still, you can I think find the circle that will inscribe zero. It will be a rough approximation. But
yes, you can. Of course, you can any figure describe a circle. Okay. Another questions. Last questions.
Maybe you come back to that. But as for now, I have a question about the implementation side. So you got the various gains, right? So a lot of different gains from
Yes.
this procedure. Which is like each gain is somehow mapped between the state. So you have a state, you measure the state, and now you have some mapping between the state and the gain that you should apply. Did I get that right?
Yeah. Okay. We speak about, yes, my example was very similar to regulation, but it's a task of trajectory tracking. We, for example,
This blackboard is not on in the camera, I think.
yeah. I know a good example. I have a good example in next slide. In this picture, it's a pendulum around upper equilibrium with contact wall. And first, Zonotopes this, and we should find trajectory that converge us to 0. And here you can see how it's happened. And you want to converge from this point to this, and for example, 100 steps. And after that, you get a policy for each step. And with some discretization, you know your discretization of your control, and you get policy, time-dependent policy.
Okay, it's not a map between state, it's map between time.
Yes.
And which
In this form,
feedback you should have.
in this form, yes.
Okay.
It's time-dependent control.
But I have a question in the picture. Like from the picture, it hit the wall.
At this moment, look on the first picture, not on
Yeah, on the first picture, it's supposed to like not hit the wall, but it hit the wall because.
Wall is not a constraint. You can push the ball. It's a hybrid control. You can find a trajectory that push elastic wall and move through this hybrid switch. Another questions?
What was one branch?
What? 1 second later, I explained another.
So just a bit confusing now about this part of that you need to find the feedback gains rather than apply the pre-compute forward. It will come a more robust, or why do we need to do this? So it looks like, okay, you calculate the number of, you calculate the sequence of feed forwards, then you get the feedback gains from them. And now you apply this feedback gains each on each time step. So how come this is more providing some stability or providing some what's the goal? Why do we need to find the feedback gains rather than apply this that will guarantee that still you will
Yeah, I can answer. Because this approach can give for us time where can give for us feedback gains that for time variant systems with constraints satisfied. And later and future steps, we go from this simple form to form that I show at first slide when this in this sets, and we need these tricks for find solution for much complex systems.
If you allow me, just one other comment. When we go from just applying feed forward to computing feedback gains, what we also have is first of all, some way to calculate or estimate stability, right? So with feed forward, you cannot really estimate your stability. With feedback gains, you can try at least, right? Second, we only compute, let's say, 20 or 30 or 100 steps forward. So that will be, piecewise constant control. With feedback gains, what we could try to do is have a high frequency feedback control with a changing gains. So it becomes very close to what they call gain scheduling, right? And we can discuss stability benefits of those systems theoretically, but also I think it might be important to discuss them in terms of like practicality. Just the ability to apply them on a higher frequency can do something for us in terms of time lag, etc. Just the
So it is pretty similar to the explicit MPC, right? When you
Yes, it's just explicit MPC. It's one of realization of explicit MPC.
But for now, it's in time domain, not in this.
And this step in time, but in future we finished with time-free approach.
So is the U the control input or the feedback input?
U is control input for generator in feed-forward form, but after this optimization, we can find feed-forward gains in form multiplication between delta k and sub-inverse gk. Answer to similar questions. I take these pictures from MIT paper, Lmi and Drake, and they built from this convex optimizations a tree of solutions for a big area and switch between time event and time-free control, and we get a global, big global control that converts system to zero from any state. They find optimal solution for any point the conversion has to center. Okay, go. Let's continue.
There is some areas don't converge to zero. There is some areas like the green area is away from zero.
This?
Yeah.
This area converges to one of orange, and after that green converges to orange, orange converges to zero, and full system converges. Okay. Next part, it's additive disturbance. When our disturbance is Zonotope. It's very similar to previous concept, but in propagation we have not in this point, in this part, we have not just summation, but Minkowski sum. And I showed you if you previous at the board. And the propagation of our center is the same. Propagation of our generator is concatenation. And other parts the same, all the same, but main moment that size of our generator increased. If it first step our generator have size, for example, 2 by 2, and if our disturbance have 2 by 2 form 2 at each step, size of our generators increase for 2. In this moment, you can make it without order reduction, but at this moment exists some approach for decrease number of generators in Zonotopes. For example, if you have for example, if you have Zonotope in this form, you can find another Zonotopes that consist these Zonotopes and have minimum volume. For example, you can build bounding box, and you have for each Zonotopes you can find bounding box that describes this with some additional volume, and you decrease number of generators because this moment is not so good for optimization. More trivial, it's just bounding box, but exists a lot of approaches based on SVD or another techniques. We finished with first part. Another tricky moment, we can add lambda before our disturbance and add it to cost and find solutions that maximize potential disturbance. And we know our disturbance, but we need more robust, maximum robust our system, and we can describe it in this way. And it's an example. First, I try it on pendulum. Green area describe initial diapason and red final. And it's a task of maximization disturbance, and you can see in each situation system converges to final area, and after that we test it on Pendubot. Do you know this system? Pendubot is planar two-link manipulator with actuator only at first joint and the second joint is passive. Is this something described in this form?
I have a question.
Yeah.
How can we control the settling time in this approach?
Second joint in this approach?
No, control the settling time of the control system. Settling time, like convergence time.
How?
Like the time that needs that the control needs to go to the setting point that I specified.
Yes, I understand the questions. In different ways, for example, if we speak about linear system, you can take 1 second. First, empirically, you know that you need some time
yes.
for convergence. You can choose, for example, 1 second and tell that your system, tell for your system that your system should minimize cost. And
so I should put the time as a constraint. I should put the time.
No. Your time. When you first you have system in this form. You discretize your system with some dt and get discrete. And you can take, for example, 100 points it's how choose number of points, how long should be your movement. It's not the part of this lecture. It's very dependent on your task. For example, if we speak about, for example, bot, it's a non-linear system, strong non-linear system, but you can linearize it. And when you want to make some movement for pinbot, first you design your trajectory for a non-linear system. When you get trajectory, you get t. You know how long is your trajectory for time. You know discretization of your system, how fast you control, how often you control, make control actions, and you divide time of your trajectory to UDT, and you get a number of points at this.
But my question was like, if I have a constraint on the point that I need to go, like a specific time, how can I make my controller like faster or slower? How can I control the speed of the controller? Because maybe I have some constraint on the time, so I need to make my controller faster.
In this form, you can decrease number of your k.
Mm-hmm.
For example, you choose 100. Your solver gives you a solution. Okay, you say, okay, maybe 15s. Okay, and you decrease, and for example, you put, I want a solution in 5 steps, and your solver, no, I can't give you a solution that satisfies your constraints in 5 steps.
I think like he asked something related to like PD games. So there is a PD games. Like,
yes, it's just.
Here you have cost function and if it's quadratic as LQR, so design you may like increase Q or R, whatever in the LQR. Maybe in this case it will not become infeasible, but it will try to accelerate, right?
Yes.
As I understand, you suggest like try to solve it for different time steps. If it's say infeasible, okay, it's not the case when you can reach this for this.
Yes, but it's very dependent. In some cases, you can try this. You can change your cost function. You can do both of them approach work.
I think it's a pretty interesting question. Can you add some constraint based on the finite time stability, finite time convergence, so that you should ensure find such control gains that will satisfy somehow this and satisfy that some function is decreasing, always decreasing?
Yes, you describe your function in hx and you get finite time stability or reachability. In general, it's a reachability task. You can give some guarantees to reachability some moments.
If you don't mind, I think like this discussion kind of gets to interesting point in control. There are 2 styles historically, at least, to approach transient processes in control systems. One of them is to say, okay, we have like overshoot, we have time of the transient process, or the settling time, whatever, etc. Right? Those are very industry-driven ways of thinking. You would say, how long is my motor going to take before it settles, or how much it overshoots? And that is something people used a lot when they tune controllers, especially PIDs, whatever. And the second approach is like a cost function approach, which LQR uses, where you divide your cost function based on some integral function of some very simple quadratic cost. That does not involve overshoot. You cannot control overshoot directly with it. I mean, correct me if I'm wrong. You can do it indirectly, but it's like, if your function has a very tiny spike, then goes way down. Of course, it's like for linear systems, it is all simpler, but whatever. This approach is, if you want, you can think about it as a third kind of approach, or in a way, a combination, where you say, okay, not only we are going to minimize some quadratic function, but also our whole life is going to be limited to like n seconds, and within those n seconds, we are going to achieve our goal, which our goal here is to approach, final conditions, which are, Zonotope. And during this whole process, we are also going to stay within the constraints, which are also Zonotopes. So if you want, you can think about it as this approach tells you your overshoot cannot be bigger than something. And your transient process is going to be within a tube, which you defined. And your final error, steady state error, is going to be within another Zonotope. So you can think about it as some sort of combination of this old thinking and this simple LQR style of thinking, because there is both cost function and limits. But that is all, remember, that's all like game of words, right? At the end of the day, the ID control gives you linear gains. LQR gives you linear gains. This guy gives you linear gains. And if one of them can achieve something in terms of overshoot or steady state error, etc., other one can, because they provide exactly the same structure as controller. Okay, sorry for
No.
I have one question before we go to this example about the sizes. It's maybe a bit confusing about the Zonotope sizes. Did you play this? So this is you specify them, or you contract them, increase them along the. So in the end, you have some sets that you want to reach, right?
Yes.
And then,
or no, it's very different. You can describe here anyone. You can tell, okay, last Zonotopes xk should be in xn should be in some Zonotopes. Or you say it can be anyone, but cost of xn should be very low. You can add a very big qn here.
and just a bit technical question, because like when you do this optimization, certainly something is not feasible for your system, right? Some motion
Yes.
is not feasible, and your
Yes.
solver will say, okay, it's not
Yes.
feasible. So then it become a play of with this like sizes of Zonotopes and different stuff to make this happen, that you
Yes,
finally
yes.
may reach this. So if your algorithm do this for you, it's much more convenient, right? So you can say, okay, you may reach this size of Zonotope, you may reach this size,
Yes.
you may reach this tube. And the question was, so what is going on when you tune the algorithm? You just provide the dynamics, right? Some linearization, and then give you the answer. I can remain in this tube, right? Or you need to.
Or you can minimize size of your tube.
Okay. So you may say like each Zonotope should be smaller than previous, smaller or equal.
In any way, for example, you have some trajectory. Okay. Abstract system x6 dot. We start at this area, and unit converge to this area. And for example, you can tell, I want that my trajectory should be inside this. No problem. And or you can tell, okay, I want that each the absolute. No, in this form. Okay, you can tell that, okay, no, you cannot. In this approach, you cannot tell that, cannot build something like Lyapunov function, and this function should be converged. Maybe you can with something, but I never do that if you ask about that. But you can tell, okay, your Zonotope should be inside this. Or you can tell no limits, but minimize them. So how you can. Okay, I answer your questions.
Yeah, I think so. Maybe we'll discuss later on.
Okay.
Because it will be really cool if you can say, okay, contract each of them as high as you can, along these trajectories, and you can like do a lot of proofs on this.
And they do a trajectory optimization for orbital, stability, etc. But unlike FTS, where they start with theorems and they go from them to practical tools. I mean, at least if you look at the papers that are currently output, they start with the tools. And I'm not sure, how much of proofs you can get from that. Geometrically, like if you consider discrete system that goes directly from one state to the second state without any discussion of underlying nonlinear dynamics, then sure you can prove everything. But I'm not sure how much of a proofs for continuous systems.
No, I mean,
discretized.
It's just interesting. Like if you have something which smaller and smaller and smaller, you can always say this is contraction.
Yeah,
this is
contractions is relatively easy here, but you need to see let's say you go very small, and that is by the way, it's like a general point here. Let's say you have very small Zonotope, and you say from this very small Zonotope, we are going to wait with this teeny Zonotope. Problem is, from this very small Zonotope, you could escape with a very small perturbation. And if you escaped, your guarantees are only inside the small Zonotope. So for example, you could have enormous gains because the gains are designed to react to very small errors inside this tiny Zonotope. And once you're outside of the Zonotope, your guarantees go poof, right? So the game is not just to minimum contract everything, but also to make sure you are general enough, so you cover enough area. So small perturbations, which are definitely going to happen in practice, will not destroy your, your ability to cover the set, to be in the set. Sorry, you don't want small perturbations to pull you out of the set for which you designed your trajectory. Right. Sorry.
For example, for this system for Pendobot, you cannot find Zonotopes that determinant of each of them. You cannot find contraction because some of Zonotopes will increase.
Okay. Then this certainly can give you like the question was when you already implement this. So you already implement this, and you give some specifications. So you have a nominal trajectory, you have a number of LTV matrices, and so on and so forth. And what algorithm provides you? It provides you just like these feedback gains and the I think Zonotopes around the trajectory which you can reach, right? So which like assets when you will certainly be.
Yes. If you start in, if your system releases system and you start in first Zonotope, so you never reach each region.
Maybe I just confusing the Zonotopes specification or its result of the algorithm. So
it's HU. It's a HX it's your specification.
Okay.
G U.
Okay.
It's,
then you have specified. You say okay. I am in this set, and find me the like admissible feedback gains that I will be never outside of this set.
Yes.
And there is any way how to find this like maximal what is maximal invariant set?
It's another. You can do that, but it's out of this lecture. Okay. I can show it to you later, but it's out of this lecture. Yeah, come to the Pendobot, and after the pendulum, we start working with Pendobot and make this example. It's I get the solution first I find a trajectory for nonlinear system, and after that I find a feedback solution for maximization disturbance. And get swing up. Yes. We try and make it another approach, for example, LQR, and it strictly doesn't work just for down so swing up. For some situation, LQR for down swing up works, for some no, for high never. It shows on practice how this approach works. What time? Let's continue. Next step, A and B can be a set too. Main difference from previous case, we get a multiplication between sets. Before we have only summation, but now we have a multiplication between a set of our matrix and a set of our state. Yes, it first approach, we can describe our model as matrix polytope. It's a linear combination between several matrices with some coefficients, positive coefficients, with sum equal 1. I think you know this form in this formulation about convex hull. Okay, and after that, our propagation, it's a convex hull of for example, we have two matrix A, for example, 1, 0, minus 3, minus 1, and 1, 0, minus 3.5, minus 1.5. Our A is a combination alpha 1, A1, alpha 2, A2. Alpha equal 1. I think not all see what's happened on this part here. Yeah? Or not?
It's a convex combination, right?
Yes, it's just convex combination between our dynamics. And
so you can think about it in terms of what we studied as a V polytope. So you remember we had polytopes described as a set of inequalities, H polytopes, half space polytopes, and a set of vertices, V polytopes. So this is a V polytope. And here it is a convex combination. By the way, you remember a convex combination is given by this equation that Oleg brought. This constraint on the sum of all coefficients be equal to 0, or it is equal to 1. There is one last constraint that any of you remember? On alpha, the one last constraint. I mean, this is not enough to describe convex hull.
It should be -1 to 1.
It should be not from -1 to 1, but very close.
0 to
On
1.
alpha, yeah, 0 to 1. Yeah. So alpha 1, alpha 2 should be from 0 to 1, and then you get a convex hull.
So now you remember it. Okay, good. So it's very no problem. Our A is a convex combination of A1, A2. Okay, our dynamic equation xk plus 1, A xk. Then we put this part to this part and get that xk plus 1, it's a linear combination of our two dynamics. And that's all. Where is it? And we get this propagation. It's convex hull between a x and Minkowski sum with disturbance. And our optimization task. But in this case, independently of how we make a convex hull, exist several approaches, and I think it's not important in this lecture, but you can answer it. Our number of size of our generator increase very rapidly, and we need in this approach we obviously need order reduction. Yes, it's a little difference, but our feedback can't allow that change.
So I have a question here. Why do I use this kind of approach while increasing the complexity? Why do I need to use this approach, like this formulation? Because I just increase the complexity of the constraints.
Because it's more before, when we speak before, your model can this only set at additional disturbance. You tell, okay, I know our model precise, but I don't know our disturbance. In this case, you tell, okay, I don't know my model precise. For example, I don't know inertia of my system, and I don't know external disturbance, but I want solutions that satisfy some constraints. Yes, this optimization task more difficult, and after that we get a huge optimization task. It can exist in less than 1 million variables, but you get very good solutions.
I have a question. So we have A1 and A2 because we don't know our dynamics precisely. If we know our dynamics, we will have only one matrix.
Yes, I can show you another example. It's equation linearized pendulum equation in discrete form. It's the matrix A discrete. And for example, you don't know precise K mass, you know precise K, you don't know K precise, but you know that it's between 0.5 and 0.7. With A discrete with 0.5, it's A1. With 0.7, it's A2. And you get A1 and A2. And it can be biggest. For example, AM. Another question? Okay. It's a result. previous part, before we start speaking about multiplication and model uncertainties, it was not our research, it's explanation, some basics. It's based on MIT research that I showed. But this part with parametric uncertainties is part of, it's our -30 research, and it's a result. Inverted pendulum with wall. And we find limit cycles that move into modes, in free mode and in contact mode. And our uncertainties was in free mode. It's we say that position of payload can be different. In this case, mass of payload much bigger than mass of aluminum rod. It can change between some distances. And in contact mode, we do not precise know stiffness on spring and friction between. We really don't know it precise. And you can see, after optimization task, we get polytopes, red areas. And you can see here that when we contact spring, our zonotopes increased. It because we don't know parameters of spring. And here you can see two trajectories. Station with different position of payloads. I think it was 5 centimeters difference. You can see that at this point. Trajectories.
Every point of this red cloud is a zonotope.
Yes, red. It's our zonotopes after optimization task. Yes.
So what is the goal of this system?
Goal?
Yeah.
The system. We built the system for validate this theory. Or what was your question? It's very easy hybrid system. This not practically. If you speak about practically or what questions?
I was trying to basically hit a wall.
Yes.
We made an elastic wall. We were trying to hit it at a what do you call it? At a certain other trajectory. Basically, we wanted to create a trajectory that would be repeatable and so on with a collision event. And the challenge was just to, without knowing precisely the properties of the springs that were, inside this elastic wall, to generate a trajectory that would still be repeatable and executable.
This is a combination of some typical disturbances in one.
Yes. And this system is hybrid. We need some systems that should be hybrid and show how it can work with uncertainties. Yes. Why hybrid? Because it's a very easy example of something, for example, like walking. When you walk, you do have hybrid switches between when you let in fly or in stance phase. Yes. And second example is bandbot. We find the same task but without hybrid switch. And we change mass of the first link. Get this solution.
Can you briefly explain how did you tune Zoho? you have this like system or whatever first system in there. So here, as I can see, this is on the top size, they don't change at all along the whole trajectory, which should be confusing, but okay, anyway. In the first one, they did change. And why they did change, how we choose this, why is it so, and so on.
In this case, the reason of this, in this case, our Zonotopes change based on system behavior. For example, in this point, start contact mode, and influence of behavior of Spring is very big. And for example, actuator where our Spring influence of Spring much bigger than actuators because at this point Zonotopes start increase because our actuator can't control situation in this mode. And after that, system convert when contact finished, system starts converse. One big difference between this trajectories and this Zonotopes and next, and that in this case, because we use here mixed integer solver, it's a linear cost. Because for mixed integer, linear cost works much faster. And when I choose quadratic cost, that trajectories to start be very very slow changes, very accurate. But with linear cost, it's more here it's a quadratic cost, and trajectories start very accurate. How we design this, I tell that the mass of testing can be changed between some parameters, and exist some additional disturbance that can be designed by hand.
Can I, if you don't mind, give like my perspective? I mean, I think this picture is not a matter of complete understanding so far. It's more of a interpretation kind of thing. I think like intuitively you would ask yourself, why didn't they shrink, right? Well, point is, if they were shrinking, that would mean that on after let's say 3/4 of a cycle, we would only have guarantees for a very small region inside the around the trajectory.
No, not about shrinking at all. And I mean, like, why did it not change the size in the different region of space?
Why they didn't deform?
Yeah,
because it's not so difficult trajectory. My answer is because it's not so difficult trajectory.
Dynamics is very a lot along this.
No, I mean, I mean, this is probably a function of cost. Our cost, I think, was benefiting those kind of like uniform shapes. Okay. But if you go previous slide, if you don't mind, like those deformations here, at least our interpretation. Sometimes, I mean, we discussed this. It's not like we in Alex have the same thing, all those things. But sometimes we thought that maybe what happens is the specific Zonotope becomes very deformed because on the next stage, something very specific has to happen. For example, hybrid event has to happen. And in order for the whole Zonotope to experience a hybrid event, it has to be prepared. And the planner makes it in a very specific shape, which would allow it in the next step to experience hybrid event. Because, for example, you cannot allow half of the Zonotope to be experiencing hybrid event, so half be below the hybrid boundary. And sometimes you need a very, so for that, it would be easier to, for example, have a small Zonotope so it could become small. But also, velocity and position behave differently. So sometimes it is easy to make a small position error, but difficult to have a small velocity error.
I agree here. There is a lot of sense in this picture, but on next there is no.
Yeah, but it's like this picture was challenging exactly because we had this hyperthread, and on top of that, we also didn't know the model of the string. Well, on the next picture, it's kind of like at least the model was relatively stable, and the challenge was kind of the same.
Yeah, but there is still a lot of points like where you have near the singular positions where they have.
I mean, Alec, correct me if I'm wrong, but it was like this trajectory, right?
I show this trajectory.
Yeah, so we were trying to balance basically. So it was actually very simple trajectory.
So it
Very
will be
uniform.
very interesting to see this evaluation of the numbers for the spin up, because there are certainly some.
They would definitely not look like this donut shape. Swing up indeed requires a whole lot of work, and actually sometimes the solver just doesn't find a solution because it is difficult to find any guarantees around swing up.
It's this movement.
So actually,
here it's an example too with time-free control, and I catch system, and after that it starts. Or I can. It's very big, very big robustness.
Just for the students, you understand that there was no motor in the elbow joint, right? So I was kind of just trying to balance.
The same approach, the same control worked in previous situation. System was without additional mass. Here we put additional mass, and the same control works. And I think I'm using.
Do you have videos for inverted pendulum?
No, we haven't videos with inverted pendulum.
Each zonotope is a discrete element of a space, and size of zonotopes according to precise of your computations, isn't it?
Can you repeat?
Each zonotope is a discrete element of n-dimensional space, and the size of zonotopes according to precision of your computations.
It can answer them. I don't think, not really. Zonotope is just a representation of the states for which we want to, do our guarantees, our control. So let's say this is a tooling robot. So visually, you can imagine there is a ball here, and all of the states inside those balls are the states for which we currently want to have some guarantees. Of course, we are describing usually joint coordinates, but that's beside the point. And so it is a set of states, basically. The size of the zonotop depends not only on our ability to predict where exactly we are going to be, that is indeed part of it, right? But also on our, our desire to guarantee something for bigger sets. Because if we know we're here, something can happen to us, and we'll be here, or nothing will happen to us, but also we will have some disturbances or whatever in our measurements, or etc. We want basically to have guarantees not just for this exact state, but for all of those states, and that that desire kind of guides us towards the set representation. That's actually what explicit MPC is kind of all about, or finite type stability is kind of all about. You want to have guarantees not for one state, but for a set of states. And that implicit kind of like drive is what makes Zonotopes, what makes us choose bigger Zonotopes and so on. So it's kind of not correct to think of Zonotopes as just a representation of our inability to measure. If I don't know if anyone agrees with me. It's just like philosophical points, right?
And it's just very easy algorithms to switch from time-dependent control to time-free control. It's just find nearest Zonotopes and you apply, you find where is you in state space, find nearest Zonotopes and apply a policy of this Zonotopes. And when you see the video, when I put my hand and then the bot switches from this point after collision just here and continue moving. But without time-free policy, in this situation, systems fall. But with time-free control, this movement continue. I think that's all. That's all. Maybe another questions?
If there is any works, maybe not your work, but
Input output case.
Yeah, when there's not output state feedback, but input output. So you have an output y is equal cx or ck xk whatever. And how it will change here or something. It looks like it's not real at all, but maybe I confused because if it's not real, why do you need then full state measurements? So it will just provide the C and it will work.
Maybe I don't know. I don't know. We think we start thinking about it, but not make it. I not see. When I make literature review, I never seen the solution for this approach, but I think it can work.
I mean, for explicit MPC, I did test it. It does work, input output, but I didn't test it with Zonotopes. I just tested it with a bunch of feed forward. Then do the same trick with getting a gain matrix, but using C, it just works.
Because it's also a lot of practical problems.
Yeah, exactly.
All noise and all this stuff.
However, like when you start thinking about output, you also want to think about what is time delays, what is nonlinear sensors, what do sensor uncertainty or center accuracy does for you. Some of it you can represent in some sort of a part of this framework. Some of it is very difficult to represent, and I think sensor part of Zonotopes is probably one of the most challenging, interesting, but hard parts of this whole story.
Yes, this area have a lot of questions, a lot of actual tasks. Yes, it's a live actual research area.
Great. Thank you so much, Alec, and thank you everyone for listening. I want to apologize for online students in case you were asking questions and we didn't see them, because our setup was as usually very cramped. Give me a second. Okay, we didn't have any questions in the chat. Good. All right, we'll see each other on Wednesday. We'll have a lecture as usual. I apologize for making you work during national holidays, but it also means that we will have our lecture before we have to have exams. And this Wednesday lecture is very, very important. It was going to cover mixed integer optimization, which part of it you already saw today, but only part. You're going to see, hopefully, the details. And this is what is being a backbone of trajectory planning for vehicles, for quadrotors, for footstep planning for robots, and even control for hybrid systems. So it's a very important topic. And Wednesday will be our, I think, last core lecture, unless I'm mistaken. But it's a very important one. So please make sure you attend. Right.
When will be the final of the course?
I will have to ask the Department of Education for.
What?
Yeah. June 6th. Really?
So
Yeah.
we have the
I mean, I will ask DOE. I will ask DOE for when the final exam, but definitely not this week, and hopefully not next week.
Because it's just it's confusing because you said the next lecture will be the last one.
The last core lecture, the last one that you absolutely have to have. The rest will be more of a extra material that is beneficial but not completely necessary. All right. Thank you.
No, sure.